Suppose we take a group of subjects and describe to them a product and ask them how likely they are to purchase this product. The subjects respond on a scale of 1 to 7, where 1 means they're very unlikely to purchase the product, 4 means that they're neutral, and 7 means that they're very likely to purchase the product. What we're interested in is how alterations in the pricing of the product affect the subject's likelihood of buying the product. So we split our subjects into two groups. In the first group, we describe the product and tell the subjects that the product costs $30. For the second group, we describe the product and say that the retail price is $90, but that it's on sale for $30. So both groups perceive the price of the product to be $30, but one group thinks that the product is actually $90 on sale for $30, while the first group believes that the price is simply $30. The question we're asking here is whether this discounting of the price affects the subjects, thereby causing them to want to buy the product more or buy the product less than the other group. So what we're interested in is a comparison of the average likelihood of the first group buying the product versus the average likelihood of the second group buying the product. We call this a difference in means test. So we begin with a hypothesis. Our null hypothesis is that the population mean response for the subjects who saw the $30 price is the same as the population mean response for the subjects who saw the $90 price discounted to $30. The alternative hypothesis is that these two population means are not the same. So we have our data set for the first group of subjects that saw the $30 price. We can look at the responses that these subjects gave and calculate a sample mean of 4.55, a sample standard deviation of 1.504, and note that we have 20 observations. The second set of data comes from the subjects who saw the $90 price discounted to $30. For this data set, we can calculate the sample mean of 5.4, the sample standard deviation of 0.940, and note that we have 20 observations. To conduct a difference of means test, we start by constructing the test statistic. The test statistic is the observed difference in means minus the hypothesized difference in means divided by the standard error of the difference in means. The observed difference in means is 0.85, 5.40 for one group minus 4.55 for the other group. The hypothesized difference in means is 0. That is, we're hypothesizing that the population means are the same for the two groups. The standard error of a difference in means is the square root of the standard deviation of the observations for one group squared divided by the number of observations in that group plus the standard deviation of the observations in the second group squared divided by the number of observations in that second group. In this case, we have a standard error of the difference of means of 0.397. So our test statistic is 0.85 minus 0 divided by 0.397 or 2.141. So if we picture the distribution of all possible differences in sample means, we note that we've assumed that the difference is 0. We observed a difference of 0.85. And since our alternative hypothesis is that the population means are not equal, we're concerned with the area from the observed difference out toward the tail multiplied by 2. The way we measure the area is to use the t.dist function in Excel. We use the t.dist function because differences in sample means are t-distributed. The first argument in the t.dist function is our test statistic of 2.141. The second argument is the degrees of freedom. For a difference of means test, the degrees of freedom are approximately the number of observations in the first data set plus the number of observations in the second data set minus 2. The third argument is the word true, and this function returns the area from what we observed, 0.85, to the left, or 98.1%. Our alternative hypothesis is that the two population means are not equal. So what we're concerned about is this area from the difference we observed toward the tail, that is, to the right. Excel's function has given us the area to the left. So 1 minus what Excel has given us gives us the area to the right, or 1.9%. Because our alternative hypothesis is that the population means are not equal, we're concerned with the likelihood of the observed difference deviating from 0, either to the right or to the left. So we multiply our area of 1.9% by 2 to get the p-value of 3.8%. A p-value between 0 and 0.01 indicates very strong evidence for rejecting the null hypothesis. A p-value between 0.01 and 0.05 indicates strong evidence for rejecting the null hypothesis. Our p-value of 0.038 falls in this range, so we conclude that the sample data provides strong evidence for rejecting the null hypothesis in favor of the alternative hypothesis. So we would conclude here that the subjects who saw the $90 price discounted to $30 are more likely to purchase the product than are the subjects who saw only the $30 price. Excel provides another function for conducting difference of means test called t.test. T.test is somewhat easier to use. The first argument is the range of cells containing the first data set. The second argument is the range of cells containing the second data set. The third argument is a 2 if you're conducting a two-tailed difference of means test. That is, if your alternative hypothesis is that the two population means are not equal. This argument is a 1 if you're conducting a one-tailed difference of means test. That is, your alternative hypothesis is that one population mean is less than the other, or one population mean is greater than the other. The third argument is 3. This function will return the p-value directly of 3.8%.